Hello, welcome to our video solution to problem 12 from Superquiz 2. This is again from the optional section. This is a straight definition problem. The idea is, can we write down the definition of several terms using a particular set of language, namely for relations. When you have a relation from a set S to a set T, we define that as a subset of the Cartesian product of S and T. And we want to be able to use that language rather than things like, oh, it's a map, it's a rule that identifies, for each element in one set, you get an element in the other. We actually want to view all these as being subsets of some Cartesian product of sets. So let's start with function. So if you want to have a function, say, from a set S to a set T, so a function from a set S to a set T is a relation. So it's a subset of S cross T. So it's a relation. And let's call it F, because why not? So this is a subset of S cross T, such that for each element in the domain, right? That's what we call this first set. So for each S in S, there exists, well, we need a unique element in the codomain that we pair off with that element from S. So there exists a unique T and T such that the pair S comma T is an element of F. Okay, so this isn't normally how we write it. When you're, in the real world, you talk about functions, you'd write f of s is equal to t. But when we use this language of subsets, this is what we actually mean. A function is a subset of this Cartesian product. And what does it mean that f of s equals t? It means that the pair s comma t is an element of f. And to be a function, it means that for each s, there has to be some t, and there has to be exactly one t, right? You can't have s comma t and s comma u. Right? You can't have two of them in F unless t is equal to u, of course. All right, so that's our definition of a function. Okay, how about our definition of injective? So a relation, okay, well, we could just use R. It doesn't have to be a function, right? So a relation, again, we'll just say from S to T, so it'll be a subset of S cross T, is injective. So remember, injectivity and surjectivity are codomain conditions, right? So instead of starting with something in the domain, we start with something in the codomain. Okay, so it's injective if for every t in T, so we start with something in the codomain, there exists at most one S in S. Okay, so it could be that nothing gets mapped to T, that's true. But if there's one thing that maps to T, then that's the only thing that can get mapped to T, all right? That's what injectivity is all about. You can't have a picture that looks like that, right? You can't have two dots in S getting mapped to one dot in T. So for each T in T, there's at most one preimage, okay? So there's at most one S in S such that the pair S comma T is an element of the relation R. Okay, so that's injectivity. Surjectivity is going to be almost identical, except for one small change in phrase. So a relation R, again, this would be a subset of S cross T, is surjective. Again, it's a codomain condition, so we'll start with an element of T. So if for every T in T, I mean, this is, I'm just literally copying word for word until I get to this point where instead of saying there's at most one, okay, when you do surjectivity, the thing you can't have is nothing going into a dot. You have to have at least one. You could have two, three, it doesn't matter, but you have to have at least one. So we have to have at least one. Okay, so it's just one word difference. S in S such that S comma T is an element of R. It's literally a one word difference in defining surjective versus injective. Okay, but it makes a huge difference. Okay, remember, every word matters. All right, finally, we have binary operation. And this is, we have to make a small adjustment here. We don't have a binary operation from a set S to a different set T. A binary operation is always on a set to itself. Okay, and well, really a Cartesian product of a set with itself. So a binary operation on a set S. Okay, so we always just have a single set when we talk about a binary operation, is a relation, or is a function rather, right? We even know it's going to be a function, is a function from the Cartesian product of S with S to S. And there's no extra condition on it, just needs to be a function from this Cartesian product back to the set S itself. All right, you cannot really appreciate these terms, which are incredibly important in not just abstract algebra, but all through upper level mathematics, without knowing these definitions just perfectly. So take the time to learn these things word for word, to appreciate the differences between them, and you will reap the dividends.